Okay, hi everybody. So in this module, we're going to look at the first order hold. We're going to look also briefly at the circuit implementation of the digital to analog converter, analog to digital converter, and we're going to briefly talk about the sampling rate. So in the previous module, we looked at the zero order hold, and we said in the zero order hold, we take the sample, the digital signal that we're trying to convert to an analog signal, and we generate an output that is held according to the value of the sample that we have. So therefore, at the output of the digital to analog converter, we're going to look a staircase looking signal based on the sample values. Now, there is another way of implementing the digital to analog converter, and that is using a first order hold. So let's look at this first order hold. So in the previous module, we looked at the Taylor series for expansion of u of t, and we said u of t can be expanded as u of kt plus the derivative multiplied by t minus kt, second derivative, and so on and so forth. For the zero order hold, we ignored all the terms starting with the first derivative. So we approximated u of t as equal to just u of kt. In the first order hold, we're going to include a new term. We're going to include the du by dt multiplied by t minus kt into the estimation of u of t. And therefore, for the first order hold, we're going to ignore the terms with the starting with the second derivative. However, we're going to keep the first derivative in the estimation of u of t. And therefore, we're going to be implementing the equation here, which is u bar, the estimation of u of t equal u of kt plus du by dt multiplied by t minus k multiplied by t. Of course, keep in mind, again, this is an estimation of u of t. It's not, the digital to analog converter is not going to produce the exact u of t, and that should be clear because we are ignoring all these terms that come from the Taylor series. So we're only including two terms. However, we expect, since we're including more terms, to get a better approximation of u of t. Okay, so in order to estimate u of t, we need to get the derivative, this du by dt here. And one way we can implement this du of t is to calculate the slope, u of kt minus u of k minus 1 divided by t. This will give me the derivative at t equal to k multiplied by t. And therefore, I can estimate u of t to get u bar of t, and it's going to equal to u of kt plus this derivative that we said here is going to be u of kt minus u of k minus 1 multiplied by t multiplied by t minus k multiplied by t and divided by this capital T. This t is coming from here. Okay, I hope this is clear, but nevertheless, let's look at an example to make it even more clear. So again, this is the equation that we're trying to implement in order to produce the analog signal from this digital sequence that we have. So what I'm going to do in this calculation, I'm going to try to estimate the signal between 2t and 3t. So during this time period here, I have all these samples. I want to produce a continuous time signal during this time. Of course, in the actual digital to analog converter, we're going to estimate or generate the output during all the times. But for the time being, for this example, we're just going to focus on how to do the calculation between 2t and 3t. Okay, so if I look at the equation, in order to get the estimate, I'm going to have to calculate the derivative. The derivative is u of kt minus u of k minus 1t multiplied or divided by t. So therefore, the first thing I'm going to do is I'm going to come to u of kt, which in this case is equal to 2, and I'm going to calculate the derivative at this point here. And the way we're going to calculate the derivative is I'm going to take this point, which is the 2, take the previous value, u of k minus 1 multiplied by t, which in this case is equal to 1. I'm going to subtract delta y divided by delta t. Delta y divided by delta x to get the slope. So therefore the slope is going to equal to 2 minus 1 divided by delta x, which is equal to t. So therefore in this case the slope is equal to 1 over t. Now I'm going to use this slope from this time, from t to 2t, to get an estimate of how the signal that I should be generated should look like. Does that make sense? So I'm going to use the estimate of the signal that I already have, the one at t and 2t, to see how the signal should look like between 2t and 3t. Should I go like this? 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 We're going to use this slope in order to determine how the signal is going to look like. Okay, so let's see. Let's calculate first the signal, the estimated signal, u power of t. And again, we're calculating between 2t and 3t. U power of t is equal to uk of t plus u prime of t multiplied by t minus 2t. So if I want to calculate u bar at 2t, at the starting point here, is going to equal to u of 2t plus u prime of t multiplied by t minus 2t, but t that I'm calculating at is equal to 2t. So therefore, if I calculate this at t equal to tt, 2t minus 2t is going to equal to 0, and therefore I'm going to end up with u of 2 multiplied by t, which is equal to a 2. So therefore, the estimated signal when t is equal to 2t, it's just going to equal to whatever that sample value, which is equal to a 2. Okay, so what happens after when t is greater than 2t and less than 3t? Let's take a point here. Let's take this point, which is 2.5 multiplied by t. Let me estimate what the signal is going to equal to when t is equal to 2.5 multiplied by t. So I'm going to get the estimate at 2.5 multiplied by t. This is going to equal to u of 2t plus the derivative u prime of t when t is equal to 2t multiplied by t minus 2t, and the t that I'm estimating at is 2.5 multiplied by t minus 2t. And therefore, if I calculate that, 2.5 minus 2 is going to give me 0.5t, and u prime at t equal to 2t, we calculated it here, which is 1 over t. So therefore, my estimate for u of t, which is u bar of 2.5t, is going to equal u of 2t, which is 2, plus, this simplifies, the t with the 2 is going to cancel, plus 0.5, which is going to give me 2.5. So therefore, at t equal to 2.5t, my signal is going to equal, I'm going to generate a signal that is equal to 2.5 in value. Of course, it's a coincidence that I'm calculating at 2.5 and it turned out to be equal to 2.5. There is no relationship between this time and the value. Is this clear? Now, one thing just to keep in mind, when we calculate the slope, we only calculate it using at the beginning of the period. So we calculated at 2t, and we use this slope to estimate all the values between 2t and 3t. We do not keep calculating. We only calculate it once at 2t, and we use that slope to tell me how the signal is going to be going. Okay. I hope this is clear. So as you can see, instead of getting a staircase looking signal, for the first order hold, we're going to get a signal at the output that's going to have a slope to it. So this might look like this. then this might look like this. So instead of being flat, it's going to have a slope to it. Okay. Let's look next on the circuits implementation for the digital to analog converter and for the analog to digital converter. So let's look at the digital to analog converter. As we know, this converts a digital input into an analog signal. It converts the digital signal that is on my computer that I have in memory into an analog signal. And the way this digital to analog converter, if I look at the block diagram of the components of it, there is my digital input, there is some logic circuit, there is some electronic switch that are turned on and off using this logic circuit, and then I have a resistor network, and then I have a buffer that generates the output. Now one way to implement this resistor network is to use the inverted R-2R ladder circuit. So let's look at this circuit and see how it works, understand how it works. So in this circuit, if you look here, I have an op-amp, and the op-amp has a current that is I total going through the feedback resistor. So therefore the output is going to equal to I total multiplied by R. This voltage here at the inverting input of the op-amp is 0. So therefore the voltage at the output is going to be I total multiplied by R. Now, all of these inputs that I have here are going to be either connected to an actual ground or to a virtual ground. There's a switch here, or there are switches here to the input. And these switches are going to either connect each one of these to a ground or to the op-amp. But in both cases, the voltage here at the other node of this resistor is 0 volt. The voltage is all at these points is going to be a 0 because it's either the ground or it's connected to the op-amp, and the voltage here of the op-amp is a 0. So this voltage is a 0, this voltage is 0, 0, 0, etc. Okay. So if I look at this I total is going to come from all the currents that are fed to it or inputted to it to the inverting input. These currents are going to be coming from these two R resistors. So if I connect the switch here like this, this current is going to be added to I total. Again, if I connect this switch to like this is 2R. This current is also going to be added to I total. I total is going to equal this current plus this current. Whatever current is connected to the op-amp is going to make up the total current. And therefore, we can say that I total is going to equal IN minus 1 plus IN minus 2 plus all the way to I0. IN minus 1, IN minus 2, all the way to I0. Now, what we want to determine is the value of these current IN minus 1 all the way to IN minus 0. Now, these currents are going to be either a 0 if the op-amp switch is connected to the ground, or it's going to have a value that is going to go through the op-amp. So again, if this switch is here, then I0 is going to equal to a 0. There is no I0 that's going to go to the op-amp from this resistor. However, if I have it connected here, then I0 is going to contribute to the output voltage and by contributing to I total. Okay. So let's look more closely at this circuit and see how it works. So if I look at the circuit, and for the time being, just removing the op-amp, I realize that this circuit is going to look something like this. Now all of these are grounds, and the values are 2R, 2R, R, 2R, 2R, R, 2R here, R here, 2R here, R here, etc. Now what does that mean? If I look at the current, let's calculate this current here, IN minus 1. I can look at this circuit and take the equivalent of all these resistors. 2R and 2R in parallel, these two are in parallel, they're going to give me an equivalent that is R. If I add it to this R, I'm going to get 2R. If I take the parallel of this 2R with 2R, I'm going to get an R. And this is going to keep continuing like this. Here I'm going to have 2R. With 2R, these two in parallel, I'm going to get an R. R plus R is going to become 2R. In parallel with 2R is going to equal to 2R, and 2R is going to equal to R. Therefore, the current that is coming through this VR is going to equal to VR divided by R. Does that make sense? So again, I can make the equivalent of all this to be negative VR and then just an R. And therefore this current, although the direction is going to be this way, is going to just equal to VR divided by R. Now this current that we just calculated is going to split between here and here. How is it going to split? We said the equivalent of all these currents, of all these resistors, is going to give me 2R. So the current is going to split equally. Half of it is going to go through this 2R resistor, the other half is going to go this way. So therefore, if I calculate IN minus 1, is going to equal to VR over R, this current, divided by 2, because half the current is going to go here, the other half is going to go here. And if you want to verify it, just please calculate and simplify these resistors, and you should, see it if it is still not clear. But again, the idea, these two add up together to R. With R, gonna become 2R again. 2R with 2R, gonna become an R. With an R, 2R with 2R is gonna become an R. R with R is gonna become 2R. With 2R is gonna become an R. And that will give me the total, the current that is coming from this voltage source. This current is gonna split equally between this branch here and this branch here. And therefore, IN minus 1 is going to equal, the current is going to equal VR divided by 2R. Okay. Now, if I want to calculate IN minus 2, we can use the same logic that we just did. And therefore, if I want to calculate IN minus 2, I'm going to take all the equivalent of the resistor to the right of this 2R, where IN minus 2 is going to pass. And that's going to be R with these two together, R with R, 2R with 2R in parallel is going to be an R, and there's an R in here, so it's going to become a 2R. Therefore, I'm going to get the equivalent circuit that looks something like this. Okay, now if I look at this circuit, I can see that IN minus 2 is going to equal to VR over 2R multiplied by 1/2. Why? Because we said the total current is going to split equally at this node here. So this other current that is coming this way is going to equal to this current, which is VR over 2R. Now this current is going to split equally between this branch and this branch here. And therefore, that's where I got this 1/2. Does that make sense? So this current, IN minus 1 VR over 2R, is equal to this current that I have here. This current is also VR over 2R. Now this current is going to come equally from here and from here at this node here. Since this resistor 2R and this resistor is 2R, this current, the VR over 2, half of it is going to come from this resistor here, the 2R, and the other half from this 2R. And therefore, this IN minus 2 is going to equal to 1/2 multiplied by VR over 2R. Okay. So therefore, I can see that I can continue with this, the calculation of these currents. IN minus 1 we calculated above is VR over 2R. IN minus 2 is 1/2 VR over 2R. I can calculate IN minus 3 is going to equal to 1/2 multiplied by VR over 4R, which is 1 over 8 R multiplied by VR, and all the way to I0 is going to equal to 1/2 1 over 2 to n minus 1 R multiplied by VR, which is equal 1 over 2n multiplied by R. So therefore, depending on whether I switched this resistor on and off, is going to determine the total current contribution. But you can see that the contribution of each current depends on the position of that current. So therefore, the currents will only contribute to I total if the respective switch Bn minus 1 to B0 is connected to the op-amp. So again, this is the switches that we're talking about, B0, B1, all the way to Bn minus 1. And therefore, that will determine the current that is going to be contributed, and that will determine the voltage. And again, the output voltage is going to equal the summation of that current multiplied by R. Okay. Okay, now the next thing we're gonna also look at is the circuit for the analog to digital converter. And remember the circuit for the analog to digital converter, we are taking an analog signal and we're converting it into a digital code word. And if I look at the block diagram for the analog to digital converter, I'm going to have a sample and hold, and then I'm going to have a converter. The sample and hold is not the zero order hold we're talking about before. This is just a sample and hold, and we'll see how it works in a second. Okay, so the sample and hold S/H is responsible for freezing the value of the input at the sample instance t equal to kt. So if I look at this circuit here, if I have an input here, this is my sample and hold. What is the idea? If the switch is closed here, then whatever voltage I have applied to this circuit is going to appear across this capacitor. So if the switch is closed, I will be tracking whatever voltage is applied at the input. If the switch is opened, then this capacitor is going to maintain the last value that it had on it. It will maintain the value of the input before the switch was opened, and therefore it's going to hold that value till the switch is closed again. Does that make sense? So the idea again is every t second I'm going to be closing the switch to take the sample of the input value, and then I'm going to open the switch. I'm going to hold that value till I do the conversion, and then I'm going to close it again to get a new value, and so on and so forth. Okay. So let's look at how this works. Again, we have the two modes, the tracking and the hold. When the switch is closed, we are tracking. When the switch is opened, we are in the hold mode, which means we have the value, the last value that we had of the input held at the capacitor and constant to the converter circuit. Okay. So then, after that block, after sample and hold, we have the converter block. And what the converter block is gonna transform the constant voltage, E bar, that was across the capacitor into a digital code word. And the way this works, one of the circuits to do the converter is the successive approximation converter. So if I look here at this circuit, I have the successive approximation register, I have a clock, I have digital output, I have a digital to analog converter, and I have an estimate of the voltage. So let's see how this works. So at time t equal to kt, the sample and hold is gonna sample and hold the value of E of t, so that E bar of t is gonna equal to Ek multiplied by t. Now then, the successive approximation register is going to turn on the most significant bit, Bn minus 1, and is going to generate an output that is going to be converted by the digital to analog converter, and is going to compare the estimated voltage that is generated by the digital analog converter with E bar of t. So it's going to compare this input, the two inputs of the op amp. If V estimate is less than E bar, then is the most significant bit is left on. Otherwise, it will be turned off. Then the successive approximation register is going to turn on Bn minus 2, the next bit to the most significant bit, and it's going to do the same thing. It's going to calculate V estimate. If V estimate is less than E bar of t, is going to keep Bn minus 2 on. Otherwise, it's going to switch it off. And then it's going to do this n times for all the bits from 0 to n minus 1. We have n bits. It's going to do it for each bit. And therefore, it's going to determine all the bits that needs to be turned on in order to get the digital code. And of course, it's going to do this before the new sample comes in. So all this calculation is going to happen before a new sample comes in. And that will give me the digital value that will convert the analog, that will approximate the analog value. Okay. Okay, so this is the description of the operation as we talked about. After in comparison, the SAR will indicate all the bits which must be turned on and therefore produces the desired code for that sample value. Okay. Okay, the last thing we're going to talk about in this module is the sampling and reconstruction. And we're going to talk about the sample rate selection. As we will see throughout this course, the sampling rate is a fundamental problem in digital control, just like it was in digital signal processing. And for digital control, we might be tempted to sample as fast as we can, take as many samples in my circuit as we can. However, this is not always advisable. And the reason being is that the more samples that you're gonna take, the higher the cost of the analog to digital conversion, because you're gonna be demanding more calculations of your circuit, and therefore faster sampling rate means more calculations, and therefore means higher cost of the analog to digital conversion. And also because sometimes sampling might add sampling at a higher rate or beyond the acceptable rate might add no value, no additional information to your design or to your control system. So again, there's an optimal sampling point that you can select that will reduce the hardware cost and will give you all the information that you need. Sampling beyond that, you're going to be getting more information that adds no value, but at the same time paying a price for the hardware cost that you're going to have to implement. Now, in general, as a rule of thumb, we like to have the sample rate to be 20 to 30 times the bandwidth of the closed loop system, and we want the sample period to be 1/4 to 1/10 of the desired rise time response of the system. And again, these are rule of thumbs that might apply to some systems, might not apply to others, but we can always consider them as the starting point for determining the sample rate. Okay, so we're going to stop here. And again, I chose to type in this because there isn't much math and derivation in it, and I thought it might be easier to just type it ahead of time and just go over it. I'll let you read through it and hopefully understand it. What we're going to be doing next, now that we looked at the analog to digital conversion, looked at the analog to digital conversion, digital to analog conversion, what we're going to be looking next is at the controller. So we're going to look at C of Z, and we're going to look at different ways of representing that controller, that filter, that compensator before we start the design process. So similar to what we've done with the analog digital converter, digital analog converter, we're going to look at C of Z, the controller. We're going to look at difference equation, transfer function, all delay block diagram, and the state space models to represent our controller. And then step after that, we're going to look at the open loop system, then we're going to look at the closed loop system, and then we start talking about the controller design and the performance of the system. Thank you, everybody.